I'm Jeffrey Goldberg from Agile Bits. You'll also see listed here Julie Howe and Jesse Irwin, who's actually sitting right there, though they actually haven't really had a chance to actually see what I'm going to say. And I should point out that our security team really like arguing with each other. So in a good way, but it's very much part of the process. And so I would not be surprised if they disagree with lots of stuff here. Okay, so who we are. Agile Bits, we make, no, that's not right. Okay, we make a password manager, 1Password, and until recently, we do not host your data in any way whatsoever. We have absolutely zero knowledge of what people do with 1Password, and we like this design. But there's also a need to be able to get convenient, useful sharing of data among members of teams. And so for quite a while now, we've been working on 1Password for Teams. The beta was introduced last month. And so that changes a lot of the stuff that we've had to do while we still try to keep this principle of we just don't want to know anything. So my actual job title is Chief Defender Against the Dark Arts, which was something that was decided on after we decided that what I was called internally, which was worrywart in chief, was a little too negative. So here are some things that we can worry about. Customers lose access to their data. Their data is tampered with. And secrets and private information is revealed to unauthorized entities. And of course, by unauthorized, we mean unauthorized by the customer. We do not have the power to authorize, or should not have the power to authorize who data is released to. So we work to deny ourselves any power we shouldn't have. So we can sleep better if we keep if all data is encrypted, we do not have the keys to decrypt that data, and we aren't in a position to acquire those keys. And that third point is what I'm going to be focusing on now. So roughly speaking, there are two ways that we could acquire keys. When somebody just does a normal password login to a site, they're sending their password. And so any site or service temporarily acquires a user secret that way. They hash it, but they are in a position to directly acquire a user secret. Another way to acquire a user secret is to have something like a password hash that can be used for making guesses against, that can be used for cracking. So we want to avoid not only never seeing the secret directly, we do not want to see a hash that can be used for a cracking attempt. So this is just another way of saying that. If y is a hash of p, then even though the hash function may be great, cryptographically perfect, all of the things that you expect from a hash function, it does not stop you from using y as a way to test whether you have guessed the right p. And if p is low entropy, then this can actually be a useful thing. Everyone who does password cracking knows this. Okay, so now I'm going to just talk about the things that we would want in an authentication protocol. And because until now, we've never done authentication. Everything was just local encryption. There was no interaction with our servers or services. So we actually started having to worry about authentication. So the first thing you want is that the client proves its identity to the server. That's what everyone does. We also would like the server to prove its identity to the client. This is typically what you rely on TLS for, but we would also like to have that. We don't want to leak any secrets to an eavesdropper. We don't want anything that can be replayed. We don't want to reveal any secrets. I think I've said that to the server. And we'd like to negotiate a key that can be used to encrypt the session. And finally, this thing that I keep on getting around to is we don't want the server to obtain information that could be used for cracking. So we're trying to make it so that if somebody gets our hashes, they can't do anything with it. Okay. So vanilla password login, that's the wrong, I've got the wrong comment, only one. Ignore that number 4 there. A vanilla password login only does one. Client proves identity to the server. That was supposed to be in a different slide. A password authenticated key exchange protocol does all of those things that we were looking for except for the last one. It does have something stored on the server that can be used for launching a cracking attack. And that's where that number 4 is from. Typical, there are of course different instances of these things, but the typical way of doing multi-factor authentication, so you've got a password login and then you're using something like TOTP for something else. It reinforces, it beefs up the number 1, the client proving itself to the server, because it's proving itself in multiple ways. And typically, the second factor is a one-time password. So it helps resist replays. Okay. Now, if you can't see that, the sign on that gate says, notice keep gate closed and locked. Now, as we see, the gate actually isn't locked. So we've got a real problem here. So we need to have some kind of authentication system to secure this. So we add, let's say, a combination lock to the gate, and the combination is something you know. And we can improve that by adding a lock that has a key, which is something you have. And if we really want to go to really the top-notch, best security for this system possible, we can add yet another factor. There's something you are. We could have a fingerprint scanner on that gate. Okay, that was my rant about multi-factor authentication. Point is that it is not addressing the problem we want to solve. It may be addressing some useful problems in some circumstances, but multi-factor authentication does not protect a customer against a server breach at all. And so it's a lot of extra work. We heard earlier today about the burdens you put on users by adding yet more work for them to do. Okay, so we decided to go with a PEG, a password authenticated key exchange system. We went with SRP version 6, mostly because it's sitting in a standard and it was relatively easy to implement on all of our clients. But we will hear later today about some of the things to consider when looking at different PEGs, because they're not all the same. They have different security properties, and anyway, Jean will be talking about that later today. So, we added an additional user secret. Now that's a great user secret. People can really remember that. We can just ask people to know that thing. The first two segments of it, the A3 is just a version number, and the next 6 characters is a non-secret identifier, and the rest of that is a secret. And for some reason, we're calling this whole thing an account key, because I lost the vote on what to name these things. But so that's the account key. The rest of it is uniformly generated. It's a little, I don't talk about how it's generated. Anyway, it's generated by the client on initial registration and stored locally by the client. The user is not expected to know this thing. And so this is a high entropy thing. And so our key derivation, and this is all going on client side, is we've got the user's master password, the client has that account key, the email address, the account ID, and the salt may actually come from the server during initial protocol, but no, in this case, let's just say it is stored locally. We've sanitized the master password. Just as an aside, I know that Pear's been asking for this for a long time. We pick a UTF normalization so that no matter what your operating system or your keyboard or your input decides how to represent various Unicode, we transform it into something that'll be the same in each instances, so we should actually be able to handle full Unicode passwords reliably. But that's the normalization, ignore that. HKDF, think about it as just an HMAC that that also is highly tweakable. And we use, and here what we're doing is we're actually running the HMAC on the salt itself. It's our way of combining in things like some tweaks about the version information and the email address. And we get 32 bytes out of that. And then we run this, we run that through, hey, wake up. We probably should have plugged things in to power out, didn't do that. We run that through PBKDF2, and I know I don't see him, but we had the talk yesterday about Catena. This has to happen on the client. We're doing all of this client side, and so we need a KDF that is easy and efficient to implement in a wide variety of different clients. So unfortunately, the password hashing competition hasn't resulted in stuff that is that useful for us, except possibly for Makewith. But all of the tricks about memory hardness really require a kind of coding that is hard to get into all of the clients. Anyway, then we also use HKDF, which is basically hashing together the account key, the ID, a few other things to get out something of the same length that we get from PBKDF2, and then we XOR those things together. And that is blending in the master password, the account key, and then KX is the X for the SRP protocol. If you know the SRP protocol, and if you don't know the SRP protocol, don't worry about it, but that's the key that's used. That's the client secret used for authentication. Okay. We also are deriving the encryption key from the same secrets, from the account key and from the user's master password. It just uses a different salt, and it uses a different tweak in those hashings. So, and those two different salts are completely independent. So even in the worst case, if we could recover X, we would not have anything that could be used to actually decrypt the user's data. Okay. Oh yeah, so I was going to say, okay, we're done, we solved the problem. It's nice, all that's easy. This is actually where the hard stuff comes in. So the math isn't actually all that hard. The hard stuff is, how do we store the account key? If a user is going to be connecting from multiple devices or multiple clients, we cannot transfer the account key for them. They have to get the account key from device to device. That's a task that we put on them. And now, in addition to being able to forget your master password and lose all access to your data, you can also lose your account key and lose all access to your data. So these are things that this scheme causes us to worry about. And our approaches to these are piecemeal. It's a difficult problem, and we're actually seeing in the beta period how these things are working out. When it comes to storing the account key, these are stored on the client's devices, and on some devices we're able to store them fairly nicely. So like on iOS, we can store them in the iOS keychain. That works well. On the desktops, not so much. And so really a relatively simple compromise of a desktop would allow the account key to be stolen. But the way we like to think about this is in terms of different sorts of threats. A password, if it is unique, can't actually be stolen easily. It's in your head. And sure, it could be tortured out of you, but let's say it can't. It's hard to steal. But any human usable password is going to have low entropy. When we try to encourage stronger passwords, but we know that it has to be a human usable password. It's going to have limited entropy. The account key has really strong entropy, but it's much easier to steal from a breach of a person's machine, and so instead of having factors like you have in two-factor authentication, where what you're looking at is this something you have, something you know, etc. We've all heard that. Here, what you're doing is you're looking at two different threats: easy to guess and easy to steal. And by combining these things, it means that the attacker needs to do both. They need to both steal and guess. So even though neither is perfect, the combination should be getting us the best of both. Okay. Sort of towards the end, my slides just turned into notes to myself. So how does a user move the account key from one device to another when they want to do that? Could have thought of, okay, we put it on a little dongle, but that thing would then have to work on every device and every platform that we want 1Password for Teams to work with. We certainly don't want people to have to type in that thing when they register a new device. So we use a QR code. A client that already knows the account key can represent it as a QR code, and then this can be scanned by the other devices. So users are doing it over the very local, they're doing it by camera. It's that much of not going over any network other than line of sight. Okay. And then we've got the issue of people getting locked out, people losing their account key, it becoming corrupted, the computer that it's on, disk crashes, whatever. There's lots of ways to lose this thing, and we really don't like doubling the ways that people can lock themselves out of their data. With 1Password, before Teams, the most heartbreaking user requests we get in to our support is, I forgot my master password, help me. And we can give them tips on trying to remember their master password, but we've never been able, we've set things up so that we can't do any recovery. It's encrypted with keys derived from their master password, and we never have our hands on those. For quite some time, we've actually been encouraging people to write down their master passwords and put it in a safe place. Put it in a bank vault, something like that. And here we encourage this far, far more explicitly. It's there in the UI when you register. You are encouraged to export this thing that we call an emergency kit. It contains the account key. It contains a QR code of the same thing, so you wouldn't have to type it in. And it contains a space for you to write down your master password. We, of course, even our client has thrown that away and only has calculated value, so it can't print that out for you. And if you're really concerned, you could print out two of them, or you could print this out, not writing your master password, write your master password down and put it someplace else. We haven't been running long enough to actually know how this is working. So we don't have a lot of feedback on whether people have had to use the emergency kits. And because of the way we interact with privacy, we don't know whether people are printing these things out. This is one of the good things about our approach to not knowing what people are doing is for their privacy and security. One of the negatives is that we don't actually know how well a lot of these things are working, which is why we really like these usability studies that people are doing, because that, we feed off of those. We need that information. So, so this emergency kit is something that is very strongly encouraged. And then, now for the last one, I have to actually explain to you how the sharing works within 1Password for Teams, and that's a whole talk on its own. But briefly, okay, very briefly, because I want to leave time for questions. When you share, you've got various vaults, items in a vault. All the items in a vault are encrypted with the vault key. Vault keys are encrypted with individuals' public keys. And there can be what's called a recovery group, which is basically people who can get the key for what is effectively a special recovery group can, vaults are effectively shared with the recovery group. And again, this is within your team. When you sign up for Teams, there's an administrator who sets this thing up, and the recovery group, it's not us. We do not have those keys. It's up to the team leader to designate a recovery group. And the recovery group has the keys to all those vaults. It can get the keys for all of those vaults, but by server policy and not cryptographically, they can't actually get the data that's encrypted with those keys. So we've got this mechanism of within a team or an enterprise or someone using this, the leaders can designate essentially a role that things are, that all vaults are shared with. And I think that's the last of my slides. That's as far as I got, which is good because questions are very welcome.